If you have the textbook, you'll see some definitions of mathematical modeling and some other examples that you can consider. We're going to look at an example this time of ice formation and how studying the underlying processes leads to a mathematical model. The scenario we're going to look at is ice that's forming on some kind of lake. What we know about ice freezing, or water freezing into ice, is that the surface freezes first, and that's because it's losing heat to the cold air, changing state then. Then as the heat travels through the ice, so the water underneath carries some heat, and that also wants to escape to the cold air, or flow to the cold air. However, the ice that's already formed acts as a barrier, it acts as an insulator. And so we can lose more heat, but the more ice there is, the slower that heat is going to radiate out. What that'll lead us to is a model for y of t, the thickness of the ice over time. We're going to capture the insulating property by noting that the rate at which the ice forms, well, that would be a classic dy dt, is proportional to the rate at which heat escapes from the water. Okay, so that's proportional to the rate of heat escape. However, the rate at which heat escapes from the water through the ice is inversely proportional to the thickness of the ice. So the rate of heat escape is proportional to 1 over, that's the inversely proportional, to the thickness of the ice. Well, we can chain proportionalities, and we will end up with dy dt is equal to a constant times this rate, but that's a constant times 1 over y. So we're going to have a differential equation like so. The rate of change of the thickness of the ice is a constant times 1 over the current thickness. The thicker this is, the less quickly ice forms. The smaller this multiplier will become. So that is a differential equation for our model, and we also want to add an initial condition. So if we scan the territory here, we say time t is the tracker for the progress of time, and it's measured from the time at which the ice begins to form. So at t equals 0, we're going to have 0 thickness of ice. There's not going to be any there. That's when it starts to form. That would be our initial condition. And this would be our differential equation. That is an excellent grounding. We've turned a model into some mathematical statements. Our next step is then to solve this differential equation subject to the initial conditions. Our process for that is to separate and then integrate. So we're going to bring the y up, and we'll have k dt, and that's the separating part, and then we'll integrate. On this side we see y's with no t's, on this side we see t's and no y's. Now this is an interesting variation from some of the other integrals we've seen. Now it's y with respect to y, that'll be y squared over 2, add 1 to the power, divide by the new power. The integral of k with respect to t is just kt, and we'll add 1 constant for the whole package. That leads us then to solving for y, and we do that just by multiplying by 2, y squared equals 2kt plus 2c's, and so y is equal to plus or minus the square root 2kt plus 2c. However, we also know that y is a thickness, so in our model, the only thing that makes sense is y greater than or equal to 0, so we can scratch out that negative option for the square root. Not bad. Now this is still a general solution. This would apply to starting at any time with any thickness. However, we want the particular solution because we are given an initial condition that at t equals 0, y is equal to 0. So we go and hunt that down. We use those values to solve for c. Or more particularly, we're going to find c, or in fact, we're going to find 2c. If we sub those values in, we have y, which is 0, equals the square root of 2kt, but t is 0 as well, and plus 2c's. That very quickly gives us 0 equals the square root of 2c, or c equals 0. Leading in the end to our final answer, y is simply equal to the square root of 2kt, all together inside the square root sign. That is the function for the thickness of the ice over time. Let's add a little more detail, imagining the basic shape of this, where we talk about the thickness, and we talk about t. We know it's got some kind of square root shape to it. We're now told that it takes 2 hours to form half a centimeter of ice, and we're asked to predict into the future how long will it take to form 2 centimeters of ice. Well, what we'd expect is, let's move this down here so we can see the relationship a bit more clearly. Let's make that 2. That's a half. What we're interested in is this time here. At what point do we reach 2 centimeters of thickness? Well, we can use this information to track some of those values down, like K, and then use that to predict into the future. That is our particular solution starting at 0. We now also can add that at t equals 2, we're going to have y equals 1/2. Let's sub that in. 1/2 is equal to the square root of 2k times the time, which is 2. And that's going to let us solve for k. We do that by squaring both sides. That'll be 4k. And then we'll bring that across. K is going to equal 1/16. That leaves us with our full solution of the square root of 2 times 1/16 times t. The thickness of the ice at any point is given by this, which we can simplify a little bit to the square root of 1/8 times t. The follow-up question was, how long does it take to form 2 centimeters? What t value is going to give us a thickness of 2? Well, we sub in the values and we start solving for t. So we want y equals 2. That means 2 is equal to the square root of 1/8 of t. That'll mean 4 is equal to t over 8, or t is equal to 32. And the units we were using for time are hours. So we're going to have 32 hours required to get to the 2 centimeter mark. So as a quick summary, what we started off with was a relatively general statement, understanding about the flow of heat through water, through ice, that would lead to freezing, and a fairly simple differential equation that then modeled how the thickness would evolve over time. And with that, we can then generate very specific predictions about what's going to happen when in that scenario. And that's the kind of thing that's not at all obvious from just what we started with. That idea of modeling, generating a differential equation, and then actually producing a predictive solution is a huge step forward in terms of the number or the tools that we have to make scientific predictions.